Hello to you watching, and this is Group 7E. This is our presentation for our project titled Explainable Semantic Graph Convolutional Network for Microexpression Detection. This is briefly the outflow of this presentation. We shall begin by giving a brief introduction and then take you through the works that have been done, which are related to our project. Then we shall take you through the problem statement, and then after the research objectives and contributions, then after which we shall briefly walk you through the methodology and the results achieved by the methods we used, then the conclusions that we drew, the limitations, future works, and acknowledgement. Facial microexpressions are very minute facial movements that reveal underlying emotions for a very brief moment. And these microexpressions typically last half a second. And normally human beings try to conceal these emotions as they are involuntary, but by the time they try to conceal or hide these expressions, they have already been elicited on the faces. So there is need to detect these micro expressions as fast as possible because they reveal the true state of mind of human beings. Some of the micro expressions include happiness, anger, disgust, fear, sadness, surprise, and also the neural state. And these micro expressions have numerous applications in our day-to-day life. For instance, they are used by law enforcement agencies during interrogation to reveal actual emotions of their suspects, and also they are used in the healthcare setting, most especially by psychiatrists, to reveal the true state of mind of patients. Various models have been developed to detect these microexpressions, and one gap that has been noticed is that these models lack explainability. That is, their operation is abstract, and how a given model comes about its prediction to a given microexpression is unknown. So this project aims to develop a model that implements explainability on how a given microexpression is detected. We did our literature review and we were able to see various works that were done by various authors that also aimed to detect these microexpressions, and various machine learning models were implemented to detect these expressions. For instance, the convolutional neural networks were used. Fully convolutional neural networks were networks models based on deep learning were also used. And then some other authors used random forests with an accordion spatial temporal representation. And others also went on to implement electroencephalography and physiological signals to detect these microexpressions. And through the literature review, we were able to implement were able to determine 4 major gaps that are present. That is the complexity in extracting spatial patterns of facial microexpressions and then connecting them to derive meaning. That is the various landmarks that are elicited by the various microexpressions are very difficult to acquire and then connect them to derive a given meaning of the various landmarks. Then also the black box nature of the graph convolutional networks, whereby these networks give an abstract operation and one is not able to know how a given microexpression is detected or determined by the network. Then there were also class imbalances in the available microexpression datasets, whereby certain classes had more images than others, as we shall see in the future. And then there was lack of augmented images in the training dataset, and this hindered the model generalizability. Having determined those problems, we aimed to solve them, and we came about with 4 objectives, with the first objective being to build and evaluate a graph convolutional network model that predicts these concealable and subtle facial emotions, to implement explainability so as to overcome the black box nature of the graph convolutional networks and understand how a specific prediction is achieved, and then also to implement data augmentation techniques such as flipping and rotation to diversify the training data set so that the model is trained on multiple angles of an image. And this in turn will help us to overcome overfitting. And then lastly, we aim to perform synthetic minority oversampling technique, commonly known as SMOT, and synthetic majority undersampling, commonly known as smooth on the datasets, to overcome the challenge of class imbalances among the 7 macro expression classes. And after we did our training and our model evaluation, we were able to develop a graph convolutional network that implemented explainability when our given macro expression is detected. We performed the smooth and smooth techniques to overcome the challenge of class imbalances, and we also implemented data augmentation on the discussed macro expression class that had the lowest number of images to increase the number of available images. So as we can see, the methodology that we used for our project, we first did our image processing, whereby we acquired our data that had the various images for the various macro expressions, and then we implemented augmentation on the images, after which we passed it to our model for training. And during our model training, we acquired the various features or the landmarks on the faces of the images, and these landmarks were passed through the convolutional layers, which then gave an output to determine that such and such landmarks correspond to such and such a micro expression, after which we evaluated our model using the validation dataset to assess whether it could correctly classify the images in the validation dataset, after which we were able to implement model explainability. Then these are the results that we acquired during the SMOT and smooth techniques that I've earlier on mentioned, whereby originally these are the datasets, the training datasets and testing datasets that had their class imbalances, and after performing the SMOT and smooth techniques, we were able to solve the issue of the class imbalances, and all our classes were balanced. Thank you very much, and let me invite my colleagues to take you through the other parts of the.
Sir, in addition to what my colleagues have presented, I'm going to carry on from the data augmentation step. So the visualization before you is a representation of our images after augmentation. As you can see, some of them are flipped, some of them are inverted, some of them are zoomed in, others are zoomed out. First of all, augmentation was done in order to improve the model's generalizability. When it takes in different images from different angles, so that it doesn't overfit on a particular way of entering images, maybe directly in front of the camera. So from other angles, flipped and rotated, it should be able to read the micro expression. Additionally, augmentation was done as part of the SMOT and the smooth analysis in order to increase the number of images in our underrepresented discussed dataset. And then the next slide shows the results and confusion matrices of both LINET and ResNet architectures as used in the graph convolutional network. So from here you will notice that the graph that the LeNet architecture performs much better than the ResNet architecture. This can also be seen in the performance metrics, where the LeNet architecture, using the same graph convolution network, achieved 98% accuracy, while the ResNet architecture achieved 61.7% accuracy. Then other models were the convolutional neural network and the recurrent neural network, then decision trees and random forest, which achieved 78%, 61%, 59%, and 27% respectively in terms of accuracy. And this graph compares the performance of our two best models, which are both graph convolutional networks, however, using different architectures, LeNet and ResNet, and still it can be seen that the LeNet architecture achieves less loss as it progresses and higher accuracy compared to the ResNet. However, it was easier to implement explainability in the ResNet architecture, which is what we did. As I'll later take you through, we used we employed GradCam with TF explain in our LeNet architecture, ResNet architecture, sorry. So this visualization is a representation of explainability results with GradCam. So the facial heat maps show what the model based on to classify the facial expression as it was classified. So GradCam works as follows. So after training, the model is fed into GradCam. That's the first step. It takes in the trained model, and then it computes. So as it runs, it computes the gradients of the target class output using backpropagation with respect to the feature maps of the last convolutional layer. It also takes in the very last convolutional layer, and then the gradients indicate how much each feature map contributes to the final prediction. The gradients are then globally averaged to obtain the importance weights for each feature map in making the final prediction from the target class. And then a heat map is generated by taking the weighted sum of the feature maps, where the weights are the importance weights calculated, and then the heat map highlights regions of the input images that are most important and most relevant for the model's prediction of the particular facial expression. Then finally, the heat map is overlaid over the input image to visualize which parts of the face have been based on to predict the facial expression. So briefly, you can see that angry considers the area between the eyes, then around the lips, and just around the nose. Then fear considers the eyes, I think the dilation of the pupils, and then the mouth, and then surprise also considers the eyes strictly. The neutral area around the above the eyes, and then the lips. Then sad considers the eyes and area below the nose and just on the side of the lips. Then fear also takes in the area around the eyes, considers the area around the eyes and how wide the mouth is open. Then as we conclude, our model was first of all able to detect various micro expressions, and we're able to also implement explainability to determine how the detection was made, the facial image detection was made. Then additionally, we were able to solve the challenge of class imbalances by using data augmentation. And finally, we trained a model that can be used in human and human machine interactions, in human to human, in things like Medicare, counseling, and also in security interrogation, to be able to tell who is lying and who is telling the truth. And we faced a few limitations. First of all were issues with the dataset, where the most common used for such work are the SAMM and CASME2 and FER 2013. We considered FER 2013 because it had a diverse number of images, and they weren't varying a lot in quality. However, it was also a challenge because some were varying, and we had to eliminate these as we were carrying out the SMOT and the SMOS. And then the expressions, the images didn't show, some of them didn't show great diversity of the expressions. And then using graph formation networks to detect micro expressions is also not an easy task because of the subtle nature of the facial expressions. So as I conclude, among our future works, we plan to use transfer learning and domain adaptation, and then to also incorporate recurrent neural networks and temporal convolutional networks. We also plan to deploy using other methods, and this will be done after reducing the model size to make it and making it more scalable. And finally, we would like to thank you, Mr. Galiwango Marvin, our lecturer, for continuously mentoring us during our model development and helping us with the different corrections and guiding us on what to do and what to correct. We really appreciate you, sir. Thank you so much. This was Group 7 evening class.